Ever wish you could like swap out parts of your code, as easily as changing channels on a remote?
Oh, yeah, for sure.
That's the kind of elegance we're talking about today, right? With a bridge pattern in C++ there.
That's a great analogy. The bridge pattern really is all about, giving you that flexibility to modify parts of your code independently, making it much easier to maintain and adapt as you go.
Music to a coder's ears, am I right? So we're diving into some slides today by Roberto Sheraton Kaplan. They're from a C++ programming tutorial, last updated just a couple weeks ago on October 14th. And, from what I can see here, this bridge pattern kind of tackles a really common problem in object-oriented programming, this idea of decoupling.
Exactly. You're separating what something does from how it does it. Think about those moments when, like, you've had to rewrite tons of code just because a tiny piece of functionality changed. The bridge pattern can help you avoid those headaches.
Oh, believe me, I've been there. Those were dark times. But I'm already getting a sense of why this is so important. Can we maybe jump into an example to make it a little bit more concrete?
Absolutely. The slides use a great one. Just think about a simple device, like a TV or a radio. Both of them can be turned on and off, right?
Right, yeah.
But the actual mechanism for doing that, the electronics behind it, they're probably different.
Okay, that makes sense. So the what is turning the device on or off, and the how is like whether it's a TV or a radio or how it actually does it.
You got it. And this is where Bridge steps in. It lets you separate the concept of the device itself from the specific on-off mechanism for that device. So if you need to change how the TV turns on, you don't have to touch any of the code related to the radio.
Okay, I'm starting to see the light, so to speak.
Right.
But I'm a visual learner. How does this actually look in practice?
Well, luckily for us, Roberto provided a really helpful diagram on slide 3 of these slides. It shows the bridge pattern using what's called a class diagram. It's got two main hierarchies: abstraction and implementation.
Ooh, things are about to get visual. All right, walk me through it.
So at the top, you have your abstraction. This represents the general concept of a device, whether it's a TV, radio, anything else.
Got it. So that's like our high-level idea.
Precisely. Now, on the other side, you have the implementer. This is the general idea of the action. In our example, that would be the on-off mechanism.
Okay, so one side's the what, the other side's the how, but they're not connected yet, right? That's where the bridge part comes in.
Exactly. And if you look closely at the diagram, you'll notice a line connecting extraction to implementer. That line represents the bridge itself. But it's not just a simple connection.
There's more to it.
Yeah.
Here's where I usually get lost.
Don't worry, it's actually quite elegant. That connecting line represents a special object, what we call the bridge object. This object holds a reference to the implementer and allows the abstraction to indirectly call its methods.
So the abstraction doesn't need to know how the implementer does something. It just asks the bridge object to make it happen.
You've got it. It's like having a universal remote control. You don't need to know the specific wiring of every TV to change the channel. You just press a button and the remote handles the details.
That's a great way to put it. So we've got the abstraction and the implementer linked by this bridge object. But how does this translate to those refined abstraction and concrete implementer boxes I see below them?
Those are where things get really interesting. You see, in the real world, you don't just have a generic device. You have specific types, like TVs and radios. That's where refined abstractions come in.
Okay, so if abstraction is like our blueprint, refined abstractions are the actual houses built from it.
Precisely. In our TV and radio example, those refined abstractions would be the classes that represent a specific TV or a specific radio. They inherit that basic structure from the abstraction, but provide their own concrete implementations.
So like instead of just turning a device on, the TV class knows exactly what it means to turn a TV on.
Exactly. And the same goes for the concrete implementers. They represent the specific ways those actions are carried out. Remember how we said the implementer was the on-off mechanism? The concrete implementer would be the code that actually interacts with, say, the TV's power button or the radio's volume knob.
Okay, I'm following so far. But seeing code always makes it click for me. Do these slides give us a peek under the hood?
They do. Slides 4 and 7 show some C++ code examples. And to keep things manageable, we'll just focus on the one from slides 6 and 7, our trusty TV and radio setup.
Perfect. Let's get into the code.
Yeah.
Now, I'm seeing a class called Dispositivo. That seems like it might be our abstraction. You're spot on. The Dispositivo class, which means device, by the way, defines the general methods any device should have, such as encender to turn it on and apagar to turn it off.
But I'm guessing it doesn't have the nitty-gritty details of how those methods work.
Exactly, and the reason for that is those methods are declared as virtual methods. That's a C++ way of saying, hey, subclasses, you're responsible for filling in the blanks here.
Ah, so they're like placeholders that the TV and radio classes are refined abstractions will each define in their own way.
Exactly. That's how we get that separation of concerns. So TV might have an insender method that prints TV incendida, while radio has its own insender that prints radio incendida.
This is brilliant. So we've got our device types and our on-off actions. Where does the bridge object fit into all of this C++ code? What's it called?
In this example, it's the control remoto class, our trusty remote control. And if you look closely, you'll see it hold a pointer to a dispositivo object.
Hold on, a pointer to a dispositivo. Doesn't that mean it could be pointing to any type of dispositivo? Now you're seeing the magic of the bridge pattern. That control remoto object, our bridge object, doesn't actually care if it's dealing with a TV or radio. It just uses that pointer to call the appropriate method insender or apagar.
So if it's pointing to a TV object, it calls the TV's version of insender. If it's a radio, it calls the radio's version. And the control remoto, the bridge object, doesn't need to change at all.
You got it. That's the beauty of decoupling in action. We've effectively separated the logic of controlling a device from the specific implementation of each device. This means we can add new devices or change how existing ones work without having to rewrite the entire control mechanism.
That's seriously powerful stuff. It
Mhm.
sounds like this pattern could be a lifesaver in all sorts of situations. So beyond like taming our TV remotes, where else does the bridge pattern shine in the real world?
Well, Roberto actually gave us a few more real-world use cases on slide 5. One that really jumped out at me was the example of building like a cross-platform application. That's a fantastic example. You often have this need to, do something like draw shapes, but the way you actually draw them might be totally different, like on a Windows system versus, say, Mac OS.
Right, because under the hood, they're using like different graphics libraries and all that stuff.
Exactly. So how would you use the bridge pattern to kind of handle this?
Well, if I'm thinking with my new bridge brain, I'd want to separate the idea of drawing a shape from, the actual code that interacts with each operating system.
You're right on the money. Your abstraction could be a shape class, defining common shapes like circle and square. And then your implementer would be a drawing API that has concrete implementations for each platform, like Windows Drawing API and Mac Drawing API.
Okay, so my shape classes don't need to know anything about Windows or Mac OS. They just say, like, hey, drawing API, draw a circle. And the bridge pattern takes care of the rest.
Precisely. Your bridge object would make sure the right drawing code gets called based on the current operating system. And here's the beauty. If you need to support a new platform, like, say, Linux, you simply create a new Linux drawing API without ever touching the original shape code.
Now, that's what I call elegant. It's like future-proofing your code in a way. But what about that multiple dimensions of variation thing the slides mentioned? That sounds kind of intimidating.
Don't let the jargon scare you. It's actually a really powerful concept. Imagine you're building a system with not just different devices, but also different ways to control those devices.
Okay, so we're not just talking about TVs and radios anymore. We might have voice control, mobile apps, or even those old school physical buttons.
That's the idea. And with Bridge, you can handle all these variations without creating a tangled mess of code. For instance, you could have an abstraction for device and another one for control mechanism. Then you could mix and match to your heart's content. A TV controlled by voice, a radio controlled by an app, and so on.
This is blowing my mind. So with Bridge, I'm not just separating what from how. I'm separating out all these different layers of functionality.
Exactly. And the best part, each new device or control mechanism you add doesn't, exponentially increase the complexity. You just create a new concrete class and kind of plug it into the existing structure.
Wow, I'm starting to see why design patterns like this are so important. It's not just about writing code that works. It's about writing code that's flexible, maintainable, and, ready for anything. I feel like I've leveled up my coding knowledge just now.
I love your enthusiasm. And remember, this is just the beginning. Once you start thinking in terms of design patterns, you'll find, countless ways to apply them.
So for our listeners who are itching to, try this out, where would you recommend they start?
Well, the TV and radio example is a great starting point. I have a challenge for them. Try adding a new device, like a smart light bulb.
Ooh, a coding challenge. I love it.
They'll need to create a new class for the light bulb. implement its own incender and apagar methods, and then make sure the remote control can, interact with it.
That's a perfect way to solidify their understanding of the relationships between the classes and really see the bridge pattern come to life. It's like taking everything we've discussed today and putting it into practice.
Absolutely. And who knows, maybe they'll even discover some creative ways to use the bridge pattern that we haven't even thought of.
And there you have it, folks, the bridge pattern.
Yeah.
Your key to flexible, maintainable, and, dare I say, elegant object-oriented code. I don't know about you, but I'm feeling inspired to go build something amazing. But before we wrap up, any final thoughts for our listeners? Something to kind of keep them pondering as they dive into the world of bridge design.
Remember, the real power of the bridge pattern lies in its ability to decouple your code. Always be on the lookout for those situations where you need to separate what something does from how it does it. That's where bridge truly shines, allowing you to create code that is not only functional, but also adaptable and ready for whatever challenges come your way.
Beautifully said. It's been a true deep dive today, exploring the ins and outs of the bridge design pattern. Until next time, happy coding, everyone.